We need to draw the products of these acid-base reactions, as well as label the acid base, conjugate acid, and conjugate base. To start, I would draw in all of the lone pairs of electrons or pi bonds that can be used as bases. So I'm just going to do that here in red. So the oxygen of the alcohol has 2 lone pairs of electrons. The nitrogen also has 2 lone pairs of electrons, but also has a negative charge. Which is more stable with a negative charge, nitrogen or oxygen? Well, oxygen. Therefore, nitrogen is a better base than oxygen. So we can use a lone pair of electrons on nitrogen, take the hydrogen that's on oxygen, this is the most acidic hydrogen in this compound, and break that hydrogen-oxygen bond, which leaves us with methanol, methoxide, and neutral NH3, ammonia. All right, so that means methanol was acting as our acid and amide acting as our base, B for base. So if we look at our products, well, how do we go from our products back to our reactants? Well, oxygen can act as a base, take a hydrogen from ammonia, and give nitrogen back its lone pair of electrons, meaning that this oxygen is now acting as a base, and ammonia would act as an acid. So in this case, this is the conjugate base to methanol. This is the conjugate acid to the amide species. If we come down here, we could look at it the opposite direction, which is the most acidic hydrogen in any of these species. Well, here we have a hydrogen attached to carbon, here a hydrogen attached to carbon. Both of those have pKa's around 50. They're pretty strong bonds to hydrogen. Here we have an oxygen-hydrogen bond that when deprotonated, you would have a resonance structure stabilizing the negative charge that would form. Therefore, this is a pretty acidic hydrogen. The bond between hydrogen and oxygen is quite weak. pKa is about 4, so this is fairly acidic. And then again, here we have another carbon-hydrogen bond. So here's our most acidic hydrogen, meaning this is going to act as our acid. Do we have a good base? Well, because there's a negative charge denoted here, that means there must be 3 sets of lone pairs on that oxygen. That can definitely act as a base. A lone pair on oxygen could attack hydrogen, break the oxygen-hydrogen bond to form the conjugate base of the carboxylic acid. So therefore, this is acting as our base. What do you get? We get the carboxylate, which is our conjugate base, and we get methanol, which can now act as the acid. If we were to go in reverse, the carboxylate could attack the hydrogen, break the hydrogen-oxygen bond to get methoxide, which we have in our starting material. Going down one more, let's look at the hydrogens again this time. Well, we have carbon-hydrogen bonds here. Again, pK of about 50. Those are pretty stable, really not very acidic at all. We have an oxygen-hydrogen bond of an alcohol, which has a pK of around 16 or 15. And then hydrobromic acid, HBr. Depending on how you memorize it, that has a pKa somewhere between 0 and -10. You can look it up in your book. And so this is going to be the most acidic hydrogen. What can act as our base? Well, we can draw in the lone pairs of electrons on oxygen. Oxygen's lone pair could attack hydrogen. You break the hydrogen-bromine bond to form bromide. So now the alcohol is acting as a base. Up here, the alcohol acted as an acid because we had a stronger base to deprotonate it. But here we're treating an alcohol with an acid, so it itself is acting as the base. Keep in mind, they can act both ways. So can amines. So then HBr is acting as our acid. We used one of those lone pairs to form a new hydrogen bond. Must have a positive charge on oxygen, and we're left with Br-. So bromide would be our conjugate base, and the acid is now the alcohol here. So this is our acid, and this is acting as, this is acting as our base. Bromide would be our conjugate base, and this would be our acid. Here on the bottom, there is a negative charge on this carbon, meaning it's a carbanion. So this is going to act as our base. We know that carbon is a very strong base if an anion. Could attack a hydrogen of water, which then gives us a new stable carbon-hydrogen bond, pK of around 50, and OH minus. So that means this must have acted as our base. This is our acid, water is acid. And hydroxide is now the conjugate base, and this would be our conjugate acid.